Hey there, welcome to another video. In this video, we're going to solve some exponentials. So I'm going to show you 4 different ways to do that with a basic exponential and 1 way to do that with some more advanced exponentials. So we're going to talk about what in the world it means to use a logarithm to solve an exponential without common bases. We'll discuss common bases a little bit, but I'm not going to go into this video since we've already done that. And then I'll show you some substitution techniques to deal with some exponentials that don't look exactly doable. So let's get right into it. When we say that we're going to solve an exponential equation with a logarithm, what we're doing is we're implying that on this exponential equation, we can't do this special case of finding common bases. See, we've done that several times where we had this exponential equation. We said, oh, hey, look, magic happened. And we have these common bases. And once we find the same base on both sides of our equation, we can set our exponents equal to one another. And we've done that already. This is the case where what happens if you have an exponential equation, there's no way to find a common base. Like 3 and 5. There's no way to change a 5 into a 3 or 3 and 5 into some lower base to set our exponents equal. So here's the idea. In solving any equation, you need the inverse operation or inverse function. Because exponentials have an inverse, and it's called a logarithm, it's going to take a logarithm to solve these exponentials. There are a few ways, like 4 ways that I can show you how to do this that are all equivalent. What that means is that your solution might look a little bit different than like a textbook or someone else's, considering the choice you make on how to solve this. When we get to not having just one exponential, when we have 2 exponentials, that really pares down what we can do and leads us into, well, you have to take a logarithm on both sides, and we're going to see that. So we're going to jump right into it. Here's the idea on how you solve every exponential equation in general. If you can, isolate your one exponential on one side and a constant on the other. If you can't, that means that you'll have 2 exponentials. Pick one on one side and one on the other. Now, in either case, if you do not have common bases, you are going to have to use a logarithm. So we're going to do that right here. So this is what's called not isolated. When you have something added, subtracted, or multiplied by your exponential, and that's on one side and a constant on the other, you have to remove the coefficient, or add or subtract to remove the constant. In this case, we're going to have to divide both sides by 8. This is called isolated as far as exponential is concerned. We're not really worried about the x plus 1 because that is in the exponent, and it would help if we put some parentheses around that to show this is the exponent. Now here's what's going to happen. We're going to have to choose on a basic exponential equation one of 4 ways to solve this. We can either go directly to a logarithm using logarithmic notation, or we can use a log on both sides in one of 3 different bases. I'm going to show you all of those things right now. So here's your options. I'm going to say this a couple more times, but please remember, if you have 2 exponentials, like legit exponentials with variables, this first way does not work. You cannot go directly to one logarithm if you have 2 exponentials. So here's the idea. Number 1 way we can do this is if you have 1 exponential, and we have that here, 1 exponential equal to a constant, we can solve that logarithm by going directly to logarithmic notation. We've actually seen that before. So we just identify, well, what is our base? Well, base is 3. What's our exponent? Our exponent is x plus 1, and what they're equal to is 5/8. A logarithm will rewrite that for us. It will solve for your exponent. So logarithms take the base and the exponent and separate it on different sides of your equation. So it takes your base of 3, your entire exponent of x plus 1, can you see why we put that in parentheses? So we don't lose that. So we don't actually add or subtract 1 right now. We have x plus 1 on one side. Yeah, we're going to subtract 1, but it's not from the 5/8. It's from a logarithm. And then 5/8 is the inside of our logarithm. And we're going to put that in parentheses, not because it's strictly necessary, but because when we subtract 1 here in just a moment, we don't want to accidentally subtract it from the argument of a logarithm. That's exactly what we're going to do. We have, hey, look, a logarithm will solve for your exponent. Because your exponent contains your variable, it's solving for your variable, practically. This is the easiest and most straightforward way to solve an exponential equation, if there's just one exponential, is writing this directly as a logarithm. Now, if we subtract 1, We're done. That's as basic as this gets. That's as simple as we can write this solution. And it is a solution. This is what's called an exact solution. It is not an approximation. It has everything in there, if you will. If we wanted an approximation, you'd have to plug that into your calculator. Now, some of you can't, because you cannot do anything beside a base of 10 or a base of e, like a common log or a natural log, respectively. So what could you do? If you had to approximate this, we would use what's called the change of base formula. We talked about that. It says pick whatever base you want. Well, usually a base of 10 or a base of e. And you could write this as a common log of 5/8 over a common log of 3. Remember, this goes on the numerator, the base goes on the denominator, and you pick whatever base you want. In this case, you picked a base of 10 because that's on your calculator. And the -1 comes after that ratio. So you'd plug this in or evaluate log of 5/8. Now, could you write that as log of 5 minus log of 8? You could do that. Is it beneficial? It depends. I mean, sometimes maybe, but here, if we're just trying to approximate, probably not. Just plug in a fraction. Then divide by log of 3. Get that, whatever that approximation is, and then subtract 1. You could have also chosen ln. So if we take ln and use that as our new base, we'd get ln of 5/8 over ln of 3, all minus 1, and that would equal x. These are the 3 appropriate solutions that we can get out of this. Is it okay to have any one of those? Yeah, absolutely. We're going to see that in the other 3 examples that we do. So this is the most straightforward way to solve this. Isolate your exponential and then go directly to logarithmic notation. However, this does not always work. If you have another exponential with a variable, this technique won't work because you can't go to one logarithm if you have 2 different bases. That would be a problem. If you don't have 2 different bases, you have the same base, then we wouldn't even be doing this. We'd have the special case of, hey, I have common bases, let's set the exponents equal. So that wouldn't be relevant. So let's go ahead and let's learn another technique that says, well, what would happen if we don't have just one exponential? They're all going to work, but 2 of them are preferable. So let's go to the next one. So what if we had 3 to the x plus 1 equals 5/8 again, and we don't want to go directly to logarithmic notation? In exponential equations, you can do almost anything you want as long as you do it to both sides. We can take a logarithm of both sides. Now why in the world do we want to do that? Well, if an exponential's inverse is a logarithm will undo that exponential. So let's take a logarithm. Now, the next 2 choices you have to solve these are you choose either a common log or a natural log. Most people use a natural log. A common log is a base of 10, a natural log is a base of e. Now, why do we want to do that? Is so that we don't have to go and change the base anyway. It'd already be in a base that's very usable for us for most people and their calculators. So we choose a common log or a natural log to do that. The last example is, what if you were really smart and you took a logarithm both sides with a base that inherently matches here? Well, that would be nice too. So we can do whatever we want as long as we do it both sides. Let's take a log of both sides. Let's choose a base 10 so that way we can evaluate on our calculator when we get to the end very nicely. So we would take our 3x plus 1 and our 5/8, and we would take a logarithm on both sides. Whatever base you want, right? But we're picking a base of 10 because that's on your calculator. Now, why in the world this works? On the right-hand side, you still have a constant. Logarithm of 5/8 is still a constant. On the left-hand side, though, why a logarithm allows us to solve an exponential is because it allows us, oh, this is a beautiful thing if you see it, log base 10 of 3 to the x plus 1. The x plus 1 is now an exponent on the inside of your logarithm. By the power property, you can move that to the front of your logarithm. So we would get x plus 1 times log of 3 equals log of 5/8. They're still base 10 logarithms. But by the power property, we can move that exponent to the front as a coefficient. Now, why is that useful? Well, because that's now just something I can solve for. I can solve for that x really nicely. There's a couple things I really, really want to point out to you. If you don't pay attention to anything else, this is super important. This is where almost every mistake comes from. Moving on. Number one, you absolutely have to have this exponent in parentheses when you move it to the front. It's a must. Why? Because most of the time you're going to have to distribute that, and if I allow you to write that without the parentheses, some people aren't going to see it. Some people are going to, if I don't have those parentheses there, are going to go, oh, I just subtract log of 3 and I'm done. No, you're not. You make a very important choice, and the second thing I want to bring up. So number one, you gotta have parentheses. It's a really big deal. It shows what you're actually doing. It shows you're multiplying the exponent times the logarithm. Secondly, you make an important choice here. The important choice is you choose whether to distribute or not. Here's when to distribute. Firstly, if you don't understand what I'm about to say, do it all the time. You can't really mess it up. Do it all the time, distribute all the time, and you can solve for x, not all that bad. But if you don't, if you do understand this, if you have no other x's anywhere in your equation, you don't have to distribute this. You can divide by log of 3 and then subtract 1. That would be fine. You could do that. So dividing both sides by log of 3, we have this. Wait a minute, that looks really, really familiar. It's the same thing. And if we subtract 1, we would get exactly this right here. We would get exactly log of 5/8 over log of 3 minus 1. That is perfectly fine. Now, I said also, well, wait a minute. Could you distribute? You could distribute, and it's not all that big of a deal, but I want to show it to you to make sure that you see that our answers can look different. When do you have to distribute? Again, you have to distribute if you have more than one x. If you have any other x's floating anywhere around here, you've got to distribute, combine your x terms on one side, your non-x terms on the other, factor an x, and divide. We've seen this as the fourth time that we will have seen this in this class, this idea of, oh yeah, I have multiple things I'm trying to solve for. Distribute, collect them, factor, divide. That's the idea. I'm going to show that to you. Kind of preface what we're going to do after we finish these four techniques on the next examples. So this is cool. We've already seen it. It's exactly the same thing. Now, what if we chose to distribute? Something you will have to do in some of the examples moving forward. If we choose to distribute, we get x times log of 3 plus 1 times log of 3, which is just log of 3. As always, I'm trying to train you on where we're going to get to in a little while. In a little while, what's going to happen is you'll distribute. You'll have an x term here and an x term here, maybe somewhere else. You will combine, well, you'll move your x terms to one side, your non-x terms to the other, then you'll factor and divide. That's what we're going to get to in just a little while. Here, we're kind of doing the same thing. We're getting our x terms on one side. That's this one. That's already there. This is not an x term. That means you got to get rid of it so that you can divide appropriately. We're going to subtract log of 3. I'm still keeping that 5/8 in parentheses so I don't accidentally subtract. And lastly, because we have one x term, because that's connected by some coefficient, this really is a coefficient. Log of 3 is just a constant. It's saying 10 to what power gives you 3? It's an exponent of 10 to that exponent gives you 3. It'll be some sort of decimal there. But this represents a number. We can divide by that. So if we divide both sides by log of 3, here's what we would get. Remember that when you're dividing, you can separate one fraction minus another fraction, but take a look at what you would get. This first fraction would be log of 5/8 over log of 3. Minus log of 3 over log of 3, which is 1. And that's precisely the same thing that we get right here. So, which way is better? Well, that's a personal choice, I suppose. I like to divide right here when I don't have to distribute, but if I'm not confident on knowing when I need to distribute, I'll distribute every time. There are times when this will not work. You cannot just divide it. If you have x's anywhere else, you have to distribute. I hope that's sunk in for you. Let's move on to the next way. So I'm going to start over with 3 to the x plus 1 equals 5/8. I'm going to take a log on both sides again, but I'm going to do a natural log. This is usually a very preferred way for people because it's ln, not a lot of writing, well, less than a log, one less letter every time. And also that if you ever have a base of e, a natural log automatically composes with that. Now I want you to think about that for a second. Could you use a logarithm that automatically composes in inverse with an exponential? What base would that be? And that's our 4th technique. So here we're going to choose a natural logarithm. It's a very common thing for us to do. And we would get on both sides log base e, log base e. What you do on one side, you have to do the other. It's going to model exactly like this, so I'm not going to spend a whole lot of time doing this. What this lets us do is if you have a logarithm on some exponential, it lets you move that exponent to the front as a coefficient, but you got to keep it in parentheses. So that's x plus 1 ln 3 ln 5/8. Think in your head right now, do I absolutely have to distribute this? Do I have to absolutely have it in parentheses? Yes. Do I absolutely have to distribute this? Not if there's no other x's, but if there are, then yes. So this is a choice you make right now. This is the only time you get a choice, is when you don't have any other x's. You can choose to divide right now, which I'm going to do, or distribute, subtract, and then divide, which is modeled right here. If you just change this to an ln, you get exactly the same thing. So we're going to do x plus 1. I'll divide both sides by ln 3. I'll subtract 1. Now, how in the world do we know that this and this are the same as this over here, or this right here? Well, we can still do the change of base, but only in reverse. Think about this for a second. If the change of base says that. Pick whatever base I want. Just take the argument to the numerator, base to the denominator. Pick whatever other base you want, and you create this ratio. Can we go backwards? Well, as long as we have the same base, the answer is yeah. So if we have log base e of 5/8 and log base e of 3, this is your new argument, and this is your new base of some other logarithm, provided these are the same base, which they are. So you could totally write this as log base 3 of 5/8 minus 1. You're just doing change of base in reverse. These have the same base, therefore I can combine them to one logarithm with that as the new base, that as a new argument. Same thing would happen here. You have log base 10. Hey, those are the same base. New logarithm would have a log of this would be the argument, this would be the base, exactly like that one. So they're all equivalent. They just look a little bit different. They're all valid. Pick it whatever you want. Now the last one. We already know we can do a logarithm on both sides of an equation, provided we actually do it to both sides. And we also know that like an ln composed with an exponential base e, or a common log composed with an exponential base 10, simplify because you've naturally composed an exponential onto its inverse, which is a logarithm. And that's great. Well, can we make that happen here? What if we took this and said, you know what? We know about logarithms and exponentials being inverses. What if I took a very specific logarithm? What if I took a log base 3? Now, why would I want to do a log base 3? Notice you have to do it on both sides, but if you do, Log base 3 of 3, wait a minute, that's a logarithm base 3, an exponential base 3. You've composed a function on its inverse. They will cancel out. They will give you the exponent. You could move the exponent to the front, and you'd get a 1 there. And you go, oh yeah, I remember that property. Do you remember it? Log base 3 of 3 to whatever power you have is the power that you have. That's what we're doing right here. This, no matter what you do, you're going to get just x plus 1. If we subtract 1, we get the same thing we've got every other time. This really is the same as writing this as logarithmic notation. It's just showing a little bit of more work. Either way you go, it's going to come out the same. Preferentially, you'd probably pick a common log or a natural log, because that would be very easy to evaluate on your calculator. This one you'd have to change a base, wouldn't you? You'd say, hey, I want a log base 10 or log base e, and write this as ln 5/8 over ln 3, exactly what we had right there, minus 1. So I hope I've made that make sense. These are the 4 options that you have to solve a basic exponential. Now we're going to move on, and this one's going to fall off the map, and so really is this one, because both of those deal with a very specific base. What if I have 2 bases? Well, then it would benefit us for one exponential, but not the other. And so we typically pick a natural logarithm to do this, or a common log in some cases, but most of the time, just a natural log. So we're going to come back with a couple more examples and show that. All right, now I'm not giving you a whole bunch of examples in this video. I'm really giving you only 5. And one of them like 4 different ways. But these next 2 are going to illustrate a lot of different examples kind of in one. A lot of different examples look like one of these 2. And the reason why I'm only giving you a couple is because really there's not much else that doesn't fit into one of these categories. There are some substitutions, and I'm going to give you the next 2 examples. But if you're going to solve some exponential equations, there's typically those you can isolate on one side and then do what I just showed you in the previous example. Those which have 2 exponentials but have a common base, which I've showed you in previous videos, or those which have 2 exponentials that don't have a common base. That's what we're dealing with here. So we have 2 exponentials. They certainly don't have common bases, not present and not available. You can't write a 5 as a 2. You can't write a 5 and a 2 as some other base. So that's off the table. Also, we have an inability to isolate an exponential here. Like we have 2 of them, so we can't get one of them on one side and a constant on the other side, which is why the first technique I taught you in the last example is not going to work here. You can't write this as one logarithm with one base with 2 different bases. That's not going to work. So we're on to one of the last 3 examples. Last 3, I guess, methods in the previous example. Could we choose to do like a log base 2 on both sides? Yes, you could. But what's going to happen is you'll end up doing a change of base later if you want to approximate it. So I'm gonna give you one of 2 things. Choose to do a common log on both sides or a natural log. I'm always going to do a natural log because I prefer it. Also, when we see in the next example, natural log is really nice when we match a base with a base. Now, you could have done that here, but we deal with some other issues if we end up doing that. So, not hard issues, but issues. Maybe I'll show that to you in just a bit. So let's take a look at it. So it's got 2 exponentials. We don't have a common base. We can't isolate one. The only way to solve exponentials like this without common bases are to use a logarithm. And we're going to apply a logarithm on both sides. We're going to pick a natural log. So an ln on both sides of this equation. What's going to allow us to do is move our exponent to the front. Right here is also where I always write parentheses around that exponent. Why? Because I know I'm going to move it. And if I have them now, I'll be able to move it later and not forget them. So I'm going to do a natural log. It's got to be on both sides. You don't have an option here. What you do to one side, you have to do the other. But once we've done that, we change an exponential kind of into a logarithm, and it allows us to move by the power property these exponents as coefficients, as products next to a logarithm. I've done a mistake on purpose. I want you to see it. I see this a lot when I'm grading tests and things like that. I see students who do this and they understand the property. They really get it, but then they fail to do one little thing and it leads to a lot of problems. Do you see how if I do this, this looks like a term and this looks like a term and it's not. There's a product here. This is the case, if I write it correctly, where you must distribute. I hope that you can juxtapose this with the previous example where I said, you might have to, you might not. But look, if you have x's in any other place beside this one right here, beside one parentheses, one parenthetical expression, if you have them anywhere else, you must distribute, get your x terms on one side, your non-x terms on the other side, factor this side, and then divide. So that's our necessary process for solving these. There's really not another way to go about doing it because x's are in multiple places. If we just start dividing here, we're going to make this side even worse. So distribute everything right now. That's why we put the parentheses, and that's why we're noticing multiple x's so we can make that judgment call. So we've distributed. We know that we can distribute ln2, we can distribute ln5. We're kind of doing backwards distribution, but it doesn't really matter. And now we're noticing that, okay, look, there's 1, 2 terms with x's. We need to group those so that we can factor. There's 1, 2 terms without x's. We can get those on an opposite side so that we don't have to worry about factoring those. Because they don't have x's, they wouldn't anyway. So I'm going to add 2x ln5 and subtract ln2. We're going to watch our signs, be real careful. It's really easy to make signs when make sign errors when we're moving terms around. So I've added 2x ln5. I've subtracted ln2. My other signs look pretty good. This is why we want to do it, so that we can group our x terms. Grouping x terms, every term that has an x in it, we can factor that x. Terms that don't have x's don't need that, so are on the other side. So we don't have to worry about factoring something they don't have. So factoring x, we factor x and get ln2. We factor x and get 2 ln5. This is great. This is exactly what we want, because what it does now is it creates a product for us. And how we undo products is with division. Before that, we had 2x's, we couldn't really divide it, it wouldn't be relevant. But now that we have that factored version of it, we can divide both sides by whatever that expression is. So ln5 minus ln2 all divided by ln2 plus 2 ln5. It's pretty wordy. That's lots of ln's. Can you see it differently? Could you see it differently? Yeah, you really could. Now, this is perfectly appropriate. You can do this. This is approximatable, but I do want you to see that there is some simplification possible. For instance, can you combine two logarithms with the same base if they're being subtracted? Yeah, of course. You can create one logarithm with the same base with a fraction or a quotient inside. So 5 over 2 inside of a logarithm. On your denominator, can you combine two logarithms being added if they have the same base? Yeah, you can, but you'd have to move a coefficient as an exponent. So wait a minute. This is ln2 plus ln5 squared if you move that as an exponent. That's ln2 plus ln of 25. How do you combine two logarithms being added with the same base? Well, you multiply. That plus creates a product inside one logarithm, so ln of 50. You could see that. You could certainly see that. You could even have a 2.5 there. But you could certainly see that in the back of a textbook because they combine all this. Now, if you got this and you look at that, clearly you're going to go, I made a mistake. You haven't. They've just combined some things. In fact, we could do one more. Now, I would leave it here because that's easiest to approximate on your calculator. It's going to basically be, you got an ln button. That's great. Notice something. I'm going to pause right here and just say this. Could you have done a common log and just put log everywhere and got the same thing with log and log? Yes, absolutely, and it does not make a difference. This is why I'm not showing it to you. I'm not going to repeat this, the same steps with just that word log. That's fine. What you could do though here is, because you have the same base in a fraction, I'm hoping you see it. Do you see that we can use change of base in reverse? We could really write this as a log with a base of 50 and a new argument of 5/2. Now, I don't know if that's better or worse, but that is one logarithm. Notice it's not ln anymore. You changed the base. You said these have the same base of e. I can combine this, make this my new base and my new argument, and create one logarithm. That's as concise as we can make it. There's nothing better that we can do with that, as far as I know. Now, I did say there is another way to do this. You'll see that you have to do a change of base somewhere, or you end up with something just like this. So approximate might not be the best. But from here, could you choose a logarithm with a base of 2 or a base of 5 and get the same thing? Yes, you can. I don't care which base you choose. It's kind of a whatever you want to do in it. But if we did, let's take a log base 2 of both sides. So on this side, notice what happens. This is the important side for you to see. If you choose a log base 2, you inherently match a logarithm and an exponential and compose a function with its inverse, and you are going to get x plus 1. On the right-hand side, though, you have log base 2 of 5 to the 1 minus 2x. Well, because that is an exponent, you have to solve that by moving this to the front of your logarithm, then distributing, then collecting your x terms, your non-x terms, and dividing. I wouldn't say it's better or worse. It's just different. Now, do you have to distribute? Well, I just said you did, but the reason is because you have an x here and x here, you must distribute this. We got to collect our x terms. And our non-x terms. So adding and subtracting respectively, factoring. And then dividing. I'm keeping this 5 in parentheses so that I don't accidentally subtract that 1. That would not be good. Now, that looks decidedly different as what we got right there. Is it the same thing? Yes, but it might take you some work to actually see it. I hesitated for a second because I didn't know if I really wanted to show you, but I do, because I always do every time, darn it. Look, if you change this to log base 2 of 25, so move that as an exponent, get log base 2 of 25, and then you can write this as ln 5 over ln 2, change of base, and ln 25 over ln 2, change of base. Do you notice that your LCD of ln 2 on this complex fraction, you can multiply ln 2 over ln 2. It would distribute, cancel here, and get ln 5 minus ln 2. That's that. It would distribute here. That'd be ln 2 and cancel ln 25. Here's ln 2, and this is ln 25. So it is the same thing. It just looks decidedly different. Way, way different. And that's one thing you find out with logarithms, is that sometimes what you get can look fundamentally different from someone else's answer, and they're both right, because there's lots of different techniques that are equivalent, lots of different properties that will do the same desired effect on this. And so don't really worry about it. As long as you follow an appropriate technique, what I'm showing you here, one of these two things, you're going to be fine. I hope that makes sense to you. I hope that you see that we can get a different look, but it's still exactly the same thing. All right, we're going to move on to the next one before we do our substitution. So we have e to the x plus 3 equals pi to the x. That looks kind of crazy. This is one reason why a lot of people use ln. And this one is for sure you're going to want to do that. It's kind of the same reason as using ln or log of 2 here, because you get this cancel thing going on and you deal with something with a different base on the other side, and that's okay. But with a log base e, you don't have to write that base. So it looks a little cleaner, and a natural log is something we can automatically evaluate on our calculators. So that's very nice, very convenient. So we qualify this. So we say what it looks like. Is this an exponential where you can have common bases? No, that's not going to happen. Is this an exponential equation where you have an exponential on one side and a constant on the other? No, we have two valid exponentials, both of which have variables in their exponent. So we cannot do those two techniques. We have to, we're forced to, do a logarithm on both sides. So you could choose a log base 10, y, or we could choose a log base e. Yes, why a natural log? That already has a base of e. So when we do a logarithm on both sides, and we choose that base of e in our logarithm, it inherently composes a function with its inverse. And it doesn't make the other side worse like it kind of did over here. That was a little bit tedious to work through. What it does is says this is a log base e, this is exponential base e. We know from our properties that's going to simplify, and we just get x plus 3. Do you need to move this to the front of your logarithm? You can, but it's not going to be relevant. You're just going to get ln of e to the first power. You get a 1. 1 times x plus 3 gives you x plus 3. This property is fine. You're using a property of logarithms right here to say when you compose a function's inverse, it does cancel. On the right-hand side, nothing really happens besides the fact that we have to move this to the front as a coefficient. Now, there's no distribution to do like we had to do over here because we just have that x to the first power, not added or subtracted. If I would have put like a minus 2 here, then yeah, I'd have to distribute and combine my x terms. It would look very much like this example or this example, which is why I'm not showing that to you. I've already done that. So if that had like a minus 2, we'd have to have an x minus 2 and then distribute. In this case, we're going to group our x terms on one side, our non-x terms on the other. This is telling you you're going to have to factor and divide. So I've subtracted x ln pi and subtracted 3. Now that we have all our x terms grouped, we can factor that x. And lastly, we're going to divide both sides. And we're done. That's about as clean as I can make it. There's only one logarithm, and so there's no logs that I can combine. I hope that you're seeing why we like to use ln a lot. It's a little easier to write. It's on your calculator, and it cleans up every time we see an e and compose it with a natural log. It's very, very nice. Also, you're noticing one thing. You're noticing me not really plugging in a lot of these to say, hey, what about our domain? Remember something. Our domain for exponentials is all real numbers. So it doesn't matter what we plug in to our exponentials, we're going to be able to get something out. What that means is that we're never having a domain issue. Now, the range of an exponential is from 0 to positive infinity, not including the 0. Remember that you can't plug in a number to an exponential and get 0 unless it's been shifted. So there will be some horizontal asymptote somewhere on our exponentials. What that also meant for logarithms was that your domain has to be reversed from an exponential and your range is reversed from an exponential. Let me explain it a little bit better. If your domain of an exponential is all real numbers, your range for a logarithm is all real numbers. If your range for an exponential is from 0 to infinity, your domain for a logarithm is from 0 to infinity. Is that a problem when we start taking a logarithm on both sides? Because we should always be thinking of the domain, right? Two functions are inverses on their domains respectively. So think about that. When I take a logarithm of both sides of an exponential, do I have a problem? Am I saying, oh, that could be negative? I'm not. Because an exponential can only give me out positives. It cannot give me out negatives. unless it's been shifted around, and that would be a constant added afterwards, added after your exponential. We don't have that. That's always positive, that's always positive. And so when I take a logarithm of both sides, no matter which one I do, this is always positive, this is always positive. That logarithm is saying, I need my insides to be positive. The exponential says, no problem, I can't even give you I can't even give you 0. So we're not breaking a domain issue when we take a logarithm on both sides of our exponentials. I hope that you're seeing that, yeah, I'm doing a logarithm and the insides have to be positive, but exponential's range is from 0 to infinity. That matches perfectly with the domain of a logarithm being 0 to infinity that we need to use a logarithm anyhow. That's why this technique works. They are inverses on their respective domains. Okay, I hope you're ready. We got a couple ones that look a little weird. When you see this, you see several terms, namely like 3 terms, and you have some things that say, I cannot possibly isolate an exponential here. I can't get 2 exponentials on each side, and so I will not be able to use the common basis set your exponents equal. I won't be able to use a direct take a log of both sides. I don't just have one of these, one exponential, and I can't combine them, and so I won't be able to go straight to a logarithm. Typically what you'll do here is a substitution technique. And so here's the thought process. If I've got not all exponentials, I can't isolate one and I can't make them equal, so I can't use logarithms as a common basis. I'm going to have to change it to something that's not an exponential to solve it, and then put the exponential back. So when we take a look at it, we go, all right, can I write this as something where the first term and the second term have the same exponential? Right now they don't. Right now we have 2 to the 2x and 2 to the x plus 2. Those are very different. They have the same base though. That's very important. And then a constant. Oh, you don't necessarily need the constant, but can I write at least the first 2 terms, or all the terms if you want, if there are more than that, as having the same exponential that we can substitute? So we're going to do things like use some exponent rules to rewrite these a little bit. And I'm going to walk you through that. So something like 2 to the 2x and 2 to the x plus 2. Firstly, identify what your exponential wants to be. We're probably going to work this down to 2 to the x. Well, that means I need to rewrite the first term as 2 to the x, and the second term as 2 to the x times something else, or to another power. So if I want to write the first term as 2 to the x, and the second term as 2 to the x, think about what 2 to the 2x means. 2x is 2 times x. Now, how do we get 2 times x for exponentials? Well, that had to come from an exponent raised to another exponent, because when an exponent is raised to another one, we multiply those. So this came from 2 to the x squared. Notice how this still makes 2 to the 2x. So we're just thinking through kind of the opposite of some exponent rules and writing this as something that's going to be the same as another part of my function, another term, part of that term. Now, how about 2 to the x plus 2? Well, I need 2 to the x, but x plus 2. How do I add exponents? Exponents that are added came from common bases that were multiplied. That's not right. But that is what I want second. So 2 to the 2x came from x times 2. X times 2 is 2x. 2 to the x plus 2 came from 2 to the x times 2 to the second. Notice how if I were to combine those, I would get common base. I would get 2 to the x plus 2. I would add those exponents. That's where that came from. And then minus 12. So we've pretty much accomplished what we set out to do. If we simplify that just a little bit, that's just 4. When you're trying to do a substitution, we're trying to make the first term and the second term have the same exact inside. In this case, the same exact exponential 2 to the x. And then we have these powers, whatever we have, it doesn't really matter. We're trying to get that out of there. So when we accomplish that, when we look at this and say, hey, I can rewrite these, and I can rewrite them so that I have the same exponential in 2 spots and nowhere else, well, then I'm going to do a substitution. I'm going to call that u. Now we're going to use that twice. We've seen this several times. So we know that we're going to get away from 2 to the x, and then later on we'll go back to it. Almost always what you get is going to be factorable. So get everything on one side, get it in order, first term positive, and factor it. If it's not factorable, I'm not going to do one for you. And this time I'm really not. If it's not factorable, you need quadratic formula. If it's higher than a power 2, you need another technique to solve it. But ultimately, once you solve it, you go back to the u you solve for is 2 to the x. Put that back and then continue with the logarithm. And you can do that. I've given you 4 techniques on how to do that. But most of these are factorable. If not quadratic formula, it's kind of nasty, but they are factorable most times. So this would be u plus 6, u minus 2 equals 0. We can check it, but that's going to be correct. Zero product property says keep on going. Now, you're not done. You're so close, but you're not done. Remember that we're not trying to solve for u. We're trying to solve for x, and our x is wrapped up in an exponential. We said u is 2 to the x. So if u equals -6, then 2 to the x equals -6. And if u equals 2, then 2 to the x equals 2. Now what do? Well, we think. Firstly, let's think about this one. 2 to the x equals -6. And you go, wait a minute. I thought exponentials had to be positive. That's true. And sometimes in these techniques, we get a false solution. This is not valid. Your exponential can't equal negative. Do you remember they have a horizontal asymptote to 0? They can't even get below 0 unless you start shifting them, and that's not shifted. So this right here is not okay. This right here is not a valid solution. There's no x you can plug in to make this actually happen. Now, if you went to a logarithm, you said, hey, my base is 2, my exponent is x. You end up with a domain issue. A range issue, listen, a range issue for an exponential, what you get out is a range issue. A range problem for an exponential becomes a domain problem for your logarithm. Why? Because range and domain switch for every inverse relationship that you have. As far as functions are concerned, including exponential and logarithms, this is not a valid solution. Creates a domain issue for the logarithm, a range issue for the exponential. Either way, you just can't have it. Now, what about this one? You can write this as a logarithm, or you can just think about it. These have common bases. Hey, that's kind of nice. 2 and 2 equal, which means x has to equal that exponent of 1. Now, in general, this is not what you're going to have to do, right? You're going to have to write this as a logarithm. So you certainly can, because your base is 2, log base 2 solves for that. So log base 2 of 2 equals x. Here's your base, here's your exponent. We separate those with a logarithm, and this uses a very nice property. Say you compose a function with its inverse. That's exactly what we said here with the same base anyway, and you would get x equals 1. I'm going to walk you through a couple others. What would happen if this wasn't a 2? What if this was a 1? If that was a 1, you could think about it. Just think 2 to what power gives you 1? Any base to what power gives you 1? Well, you'd have to have 0. That would bear out right here. So if I had base of 2, exponent of x, a logarithm separates the base from the exponent, puts what the exponent equals to as your argument, and says, hey, that's another property we have. Log base, I don't care, of 1 is always 0. Then 0 would equal x. Okay, what if it wasn't one of those special cases that you showed me, Leonard? What if it was like 7? What if 2 to the x equals 7? Well, logarithm still writes it as log base 2 equals x. And you'd have 7 right there. This is a solution. This is fine. You're done. You don't have to do anything more. Now, if you're asked to approximate, which you almost always are, then you could do a change of base. Pick ln. Pick log base 10. Doesn't really matter. And you can evaluate that ratio. So those are the 3 cases that we typically get when we're doing a substitution. We never get this whole exponential equals exponential without the common base. We never get variables on both sides, so those previous examples aren't really relevant for a substitution because we don't really get that. what we end up getting is something that looks like this, or the two previous ones that I gave you, and then we can go directly to a logarithm. Now, could you do ln on both sides, move your exponent and divide? You could, but it is easiest to go directly to a logarithm, and that's why I showed you that first technique in the first example that we did, so that this would become easier. So I hope that makes sense. Our real answer was 1. I just want to show that to you, just so that we're kind of complete here. All right, last one. I'll discuss one more with you, but I'm not going to solve it all the way. I'll discuss it. This last one that we're actually going all the way through, we're going to look at this and we're going to firstly recognize what it's talking about. This is an exponential equation, yes, but categorize it. Is this something where I have one exponential? Well, no. That means that I can't isolate it and get a constant on the other side and then use a direct logarithm. Is this something where I have two exponentials where I can get one on one side and one on the other side, either for common bases or for logarithms, direct use of logarithms? No, because that 5 messes it up. Actually, that 2 kind of messes up too. I can't just get one exponential on one side, one on the other, and do a log on both sides. It's not going to work. I'm going to have to do a substitution. So if I'm going to have to do a substitution, I'm going to make this so that I have the same exponential in 2 terms of my expression here, my equation. So I'm looking at this thinking, well, what's the best choice for our base? 49 looks like it can be simplified into a base of 7. So we're going to do that first. So I'm thinking, I want to write this as a base of 7. This is 7 squared. Now that's all well and good, but that doesn't help us. Why? Well, because that's 7 to the x and that's 7 to the second. I need them to be the same. But take a look at what happens. If I have 7 to the second power to the x power, I can multiply that 2 times x. But wait a minute, 2 times x means the same thing as x times 2. So could I just reverse those? Keep this in mind. If 2 times x is 2x, then if I put an x here and a 2 there, that would still be 2x. I'm really hoping that you see that because multiplication is commutative, you can have those 2 exponents in whatever order you want, and they still make 49 to the x, honestly, they still make the same thing. So whether I have 7 to the x squared or 7 squared to the x, it doesn't matter. So I'm going to choose this one because it fits what we're trying to do here. It just fits with I'm trying to match the exact same exponential in 2 terms of my equation. I also show those in parentheses to make my substitution a little bit more noticeable. So if my 7 to the x exponential is going to change into u, I've got 2, and then this becomes u squared. (11u) and then plus 5. Okay, so let's go ahead and factor that. It's going to be factorable almost all the time. Just be careful when they're not. You have to use a different technique. Check your factoring again. It's probably factorable. So this is going to factor as common mistake. You're not in x's right now, you're in u. So when you factor, you got to use the u. So we've got 1u plus 5. We've got 2u plus 1. We can double check this. That's 2u squared plus u and plus 10u. That's 11u. And then plus 5. The zero product property is going to set each of these equal to 0. Right now it looks just fine. But the next thing we're going to do, hopefully you understand this is not so fine. When we do this, right now we're going to look at this and go, wait, hang on a second. I've got 2 negative numbers here. Those cannot be solutions because exponentials cannot equal negatives. Now, I'm going to make real clear, this is not a domain issue for your exponential. You can plug in anything that you want. This is a range issue. This is saying, what can you plug in to get this output. You can't. It's a range issue. There's no way to get out -5 and -1/2 from 7 to the x. It becomes a domain issue for our logarithm if we were to try to do it. We'd get log base 7 of -5 and log base 7 of -1/2. That's a domain issue because it came from a range issue of an exponential. Hope that makes sense. If we would have had positive, now we don't, I know we don't, but if we would have had positive, then you'd be just fine. You could say, all right, this would be log base 7 of 5, log base 7 of 1/2 equals x. Please listen, this will give you a negative. That would be fine to get a negative out, but you can't have a negative inside your logarithm. That would be plugging in a negative for your exponential. That's okay, you can plug in a negative here. That'd be fine to plug in a negative, but it can't give you one out. So what you can't get out of an exponential is what you can't plug in to a logarithm. I can plug in negatives. I can't get out negatives. Can't plug in negatives. I can get out negatives for logarithms. So these would be our two solutions if these had been positive. I just want to show that to you to make sure that we saw that one more time. You could show it differently, of course. You could do a log of base 7 of both sides, an ln of both sides, and move your exponent divide. A log base 10 of both sides, move your exponent divide. You could also do change of base and get log of 5 over log of 7, or ln 5 over ln 7, same thing over there, and get a different look so that you can approximate it a little bit easier. But that's where I'm going to end on these problems is this idea. Once you get down to here, this is something we've talked about already. You cannot let them equal negatives. In this case, you have no solution. It's not possible to do. Okay, I felt bad that I gave you one with no solution. Feels like you didn't get what you paid for, even though for most of you this is absolutely free. So I'm going to give you one more, because I feel like it, and I can. So sometimes these negative exponents just go, what? And I'm stuck, and I don't know what to do. And I wanted to show how to do that, and that you can get one solution out of these. At least this one does. So let's take a look at that. 3 to the x minus 14 times 3 to the negative x equals 5. Firstly, classify or qualify it. Where does it fit? Is this one exponential? No. Can I combine those? No, not with subtraction. Do not try. You can't do it. Okay, can I get one exponential on one side and one on the other side without a constant to use common bases? No, because the 5 messes it up, and so does the minus 14. Can I get one exponential on one side and one on the other side with different bases and use a logarithm? No, because for the same reason. This is another substitution, but you have to set it up correctly. We must get the same exponential in order to substitute it, and we have to have it in 2 terms. So what are we going to do? For our techniques to work, by the way, what are we going to do? If you see a negative exponent, there's 2 choices, and this is what your textbook should say. Multiply by x to the positive 1. Oh, sorry, I said that wrong. Multiply by 3 to the positive x. You can do that on both sides, but it might be a little easier to see why you're doing that. If I should, and it's the same thing, but maybe write a little differently so you see why you're doing that. Remember that a negative exponent creates a fraction with whatever's being raised to that negative exponent on the denominator right where it's at. So this means this means 1 over 3 to the positive x. So 14 times 1 over 3 to the positive x gives you 14 over 3 to the x. This is why they're telling you multiply by 3 to the x. Why? Because this is now an equation that has fractions in it. How do you get rid of fractions? You multiply by the LCD. In this case, that's just 3 to the x. Now, do we have a domain issue by having that on the denominator? No, because 3 to the x can't even equal 0. Oh, as far as I'll ask about, you can't even equal that. So there is no problem. All we've got to do is understand that in either case, what we want to multiply by is something that makes that negative go away. Well, that's going to be 3 to the x. Now, you keep this in mind. It's got to be on both sides. Whether you do it here or here, doesn't matter. It has to be on both sides because you're multiplying an equation. So multiply both sides by whatever it takes to get rid of that negative exponent. That negative exponent means something on the denominator that needs to go away. In our case, it's 3 to the x. So we're going to multiply and then distribute. If I distribute here, I'm going to get 3 to the x squared. Don't write 3 to the 2x. Don't add them. Write them as what you're going to need for the substitution. So 3 to the x times 3 to the x is 3 to the x squared. Could you write it as 3 to the 2x? Yes, but you're going to get exactly what you got here. That's where that came from. It came from 2 to the x times 2 to the x. That gave you 2 to the 2x, which we had to write as 2 to the x squared. So this is the same thing as that, but we've written it more appropriately for our substitution to work. That gives you 3 to the x quantity squared. This, your denominator is going to cancel with that. So 3 to the x times 14 over 3 to the x, you cancel that, you get minus 14. You go, wait a minute, my substitution doesn't work. It's tricky. That's why on the other side of the equation, we had to multiply by 5 times 3 to the x. There's your other term with your 3 to the x in it. So we're going to get everything on one side because we're going to substitute and then factor. Please notice that doing it right here is the same thing. You get 3 to the x squared. You get minus 14 times 3 to the negative x times 3 to the positive x. Negative x, I'll show it. Multiplying common bases, you add your exponents. Negative x times or plus positive x is 0. 3 to the 0 is 1. You just get negative 14 either way. Personally, I think that's a little easier to see, but they do work the same. Whichever one you feel confident with, it's going to work perfectly for you. So now we're set up. We have a substitution available to us. That's 3 to the x. So we're going to substitute that and get u squared minus 5u minus 14 equals 0. This factors pretty nicely for us. If you do it right, u squared, that'd be minus 5u and minus 14. Can you see which of these is going to give us a non-valid solution for real numbers? Hopefully you say, I cannot allow an exponential to equal a negative. That's off the table. Your exponentials can't give you a negative. It's a range issue. It becomes a domain issue for a logarithm that we would need to solve that. This, however, looks really good. So I do a log of both sides. Move my x and divide. Log of any base that you want. Doesn't really matter. Log base 3, cool. Log base 10, cool. Log base e, it doesn't matter. I would move this to the front. That's one option that's very easy to approximate. Another option, use log base 10. You get log of 7 over log of 3, very easy to approximate. Or making it more concise, from here you can do a change of base and pick the base of 3 and an argument of 7 in a new logarithm. And that's exactly what we get if we went directly from our exponential to a logarithm. You say, hey, here's my base, here's my exponent. Log base 3 of 7 would equal x because a logarithm separates base from exponent. Either one of those is going to work just fine. I hope that this has made sense. I've gone above and beyond, I think, as far as our examples here. I've shown you every case I could think of to solve an exponential. So I hope that you're with me. Moving forward, we're basically done with what I need you to know with exponentials. We're going to go on to how to use them in some real life scenarios like finance and like differential equations, but only as an introduction to exponential growth and decay. So I'll see you for those videos, and I hope you're doing well.